Welcome to this channel, and today we will be talking about one of the most interesting topics in the field of ICT, that is the computer architecture and organization. And under this section, we will explore areas like Boolean logic, truth tables, and binary scaling. So without much ado, let's start the topic. So let's look at the first area, that is our everyday application of the bit patterns. When we look at the world of computers, one key uh, or one fundamental aspect of ICT is the idea of a binary digit. Computers think and reason differently, and they are quicker. Some say they are smarter, but that is an argument for another day. And they do all these things quickly using the bit patterns. Computers are machines, so they use bits. And when I call or when I talk about bits, what I mean is that bit is a system in which computers calculate and use to reason and come out with outputs so that we human beings can also utilize these outputs. So let's look at the everyday application of the bits pattern. We have the foundational infrastructure, and it talks about how data as bits allows modern computers to process, not only store, it doesn't end there. We also transmit the data that has been processed, that is to information efficiently. We also talk about the ubiquitous smartphone ecosystem, and we know how our smartphones have been optimized for platforms like social media and GPS, other friendly sites that we go to. So our in our everyday lives, that is the use of smartphone, the use of bit patterns are also important. We can also look at the interactive environment from our everyday internet browsing request, that is requesting and receiving information on the internet. These bit patterns are in play. Meanwhile, when you go onto the internet, what we realize that people don't normally notice that the key one key thing is that once you are requesting data from the internet, the data fundamentally the data is in bits, that is in its core form, that is the so right now the bits I'm talking about, we can qualify it as the zeros or one, the true or false. Because if you look at machines operate in two state format, that is it's either it is in an on state or an off state. So that is the bit system. The bit system, that is the idea behind it. That is a state whereby the PC or the computer or the machine is either working or not working. That is the only thing that a computer or a machine knows. It's either it's working or it's either it is not working. And it comes to build on it, becomes a pattern. So that represents our data that we use in our daily lives. Then logic is also an algebraic framework that was formulated by a mathematician called George Boole, and it is used in our electrical state mapping. It is also used in our core system logic. For the for the electrical state mapping, if you look at circuits, we have various tracks or various pathways in which a circuit moves. So in that way, we are talking about how signals are moved, and signals move, just as I said earlier on, they move in two states. It's either a signal is moving or not moving. Let's move on. So we've looked at the Boolean logic, and the Boolean logic is, just as I said, it is an algebraic framework that is used. It is used in our everyday lives, but mostly the computers or the machines normally use it to analyze the environment, like data processing. So we have operations that are involved because it's an algebraic framework. It is basically a mathematical concept. So we have operations that we normally work that are used in it. One operation is the AND operation, which talks about two inputs which are coming to two distinct or two different opinion, two different distinct opinions or inputs that are being executed to, or that are being merged, come out to form one output. And so if you have a signal which is in an a true state, which is one. So in the AND operation, we look at two inputs. So we can talk about an input like one or an input like zero, because the bit system is just two states, either one or zero. And so if you have two inputs, for instance, if you have A, which is 0, B, which is 0, the output will be 0. So there's a rule. The rule states that output scales to 1 if at least one input variable is 1 or both. So in an AND operation, both inputs must be 1 simultaneously for you to get an on output. So if you look at the example that we have here, if you have A which is 0 and B which is 0, the output will be 0 because they are both in an off state or false state. So if a false state and also a false state is being executed together, you realize that the output will be false because there's no, that is the logic behind it. If you have a true state and an off state or a false state, the output will still be 0. The only scenario where we will get a true state is when we have simultaneously a true state and a true state. And that is the last point that we have here. Let's move to the next operation called the OR gate. OR gate is also another operation, or an OR operation. It's another operation which is also talking about, it's just like the AND gate, but the only difference is that for the OR gate, we only need one or both gates or both operations, both inputs must be true so that we can output a true outcome. So that is, so the examples I've been given, let's go through some of them. You have A and B, both of them are 0, the output will be 0. We have A which is 1, the B which is also 0. So in here we have only one state which is coming out, or the input is true. So it doesn't matter the other state which is false. In an OR gate, the output will be true because we have only one. And if you have only one, it qualifies, or it's possible. The logic states that, or the logic behind the OR gate says that we just only need one true state so that the output will be true. So we have the NOT operation. The NOT operation is the negation or is the negative or inverted output. That is the name, or that is the other name to it. It acts as a logical inverter. Inverter here means that it flips the outcome to an opposite outcome. So imagine we have a true state. The NOT outcome of it will be the opposite or the inverted opposite outcome. So if it's a true state, it becomes a false. So the example that I've been giving, we have inputs. Your inputs, we are inputting. What are we inputting? The signal here says that the A signal is a zero signal, which is a false signal. And once we are looking at it from a not operation perspective, we realize that the output will be 1. And one thing also about the not operation is that it functions on a single input parameter. We only need only one input. We don't need two. Unlike the not, unlike the end and the unlike the end and the or. It requires or you need two states or two different states so that you can execute them together to form an outcome. Very good. So let's look at some real life examples. Or let's look at some statements which are based on this Boolean logic. And my logic is all about reasoning. So if you look at it from a real life complex scenario, we normally talk of instances whereby we make sentences like the dog is black. And if the dog is black, so you are the owner. So here, the dog is black. It is standing in for one input. The dog is black. It means that probably the dog has the color you all see is black, and that is the truth. So it's a true state. It is a statement that we are saying because we can see the dog. The dog is moving. The color is black. It's a dog. It's not a rabbit. It's not an ant. It's a dog. So it is true. So that is why normally if we have a sentence that tells us that, oh, this is the state or this is how it is, it's a true state. It is a one outcome. So, and also the dog has an owner. So probably you will be the owner because you own the dog. So in these two statements that we have here, both statements are real life statements. That is, they are true statements. So if you look at it from a logic perspective, so currently let's look at it from the logical end connector. That is the operation that tells us that we can only have a true state or true outcome or true output only when simultaneously the inputs are both true. So if the inputs are true, it makes the story or the outcome you want to portray or come out with true. So that is the outcome. So that is the scenario. So if you look at the structural mapping, table 1.8, we have here the dog is brown. But let me ask you, is the dog brown? No. So the A statement, that is the inputs. The dog is brown. The dog is not brown because the dog is black. So it's a contradiction to the general statement we made earlier, because we are saying that the dog is black and you are the owner. So the only owner the dog has is you, and the dog is black. So any other statement that is different will tell us that the statement is false and it's a zero. So the first structure, that is the map, the illustration that we've done here, tells us that 0, A, the input is 0, the B is 0. So it means that they are both false statements. So they are contradictions of the statement that we made earlier. They are contradictions of the statement that we made earlier. So the dog is brown and you don't own it. You are the owner. How won't you own it? How won't you own it? Because we are saying that the dog is black. The dog is truly black. But here we are saying that we are also making another statement which is entirely new and which goes against our premise, which is the dog is black. So right now the dog is not brown, so it is a 0. And we're also saying that we don't own the dog, which is not also true. So in the first structural grid, the input A and B are 0, which says that both statements are false. Sorry, they are false. So it tells us that the output will be false. So if someone comes and asks you, is the dog your owner? Or who owns the dog? You own the dog, but otherwise, but oppositely, somebody is also trying to portray the case that you don't own a dog. So it means that there's a case for argument. So this is what we are talking about. So the dog is brown, you don't own a dog. Both statements are not true. Also, we have the dog is brown and you are the owner. You are the owner, obviously, because we said it that you are the owner. But the dog is not brown. So only in here there are only one true input that can be said, that can be reliable, that can be true, which is the B, which is equal to 1. But the A is 0. The next one, the dog is black, is true, but you don't own it. No, the dog is black, but you own it. So the part that you don't own it is a false statement, but the part that the dog is black is a true statement. So in here, the output is also false, because we are saying that in an AND connector or AND logic, Boolean logic, the only way we can get a true output is that both inputs should be true. And that goes for the last point. The last point says that the dog is black and you are the owner, which says that both statements are true. We can rely on that statement. That's logic. Logic here what the logic aspect of it is that we are trying to look at the statement and ask ourselves questions that is outside the box, that borders our mind. That is the reasoning part of it. We as humans, we must reason to get concrete solutions and algorithms to solve our problem. And this aspect of ICT, or this aspect of computer science, or the engineering world, is also a part that we all need to play a very big role. That is analyze statements, analyze situations, so that we can come out with true and credible and reliable information. So what are the takeaways that we can take away from this, our short lesson? So far we've talked about the logic aspect of the way in which our computers think, and we discovered that hardware components, that is circuits, they are modeled around Boolean logic. That is, and we looked at some of the logic connectors. We looked at the AND logic, we looked at the OR logic, and the AND logic says that supposing we have two inputs, those two inputs can only merge to become one, and when they merge to become one, the likelihood of it becoming true is when both of the inputs are true, and that is final. There's no contradiction, there's no opposite opinion, and that is a fact. So supposing we have an argument and you are making a case for yourself and me too, the same thing. The only way we can say that we are both true is when both statements we are making are true. And the OR variable, or the OR logic, also is clear that we are saying that in here we are just looking at the case whereby at least one is true. And if you look at the takeovers, is determined, that it evaluates to one when any single monitored variable is verified. That is